Okay, so this talk is about concept of stability in abstract argumentation. This is something that actually we borrowed from structured argumentation, and our purpose is to be able to use it in the context of strategic argumentation. So I will start with a few basic notions about abstract argumentation. So you're probably already familiar with this. We work with directed graphs where the nodes represent arguments and the edges represent attacks between arguments. So I denote this with A for arguments and R for the attacks. The acceptability of arguments is usually based on the notion of semantics, where we compute extensions. An extension being a set of arguments that are jointly acceptable thanks to some good properties. So the basic requirements for defining an extension are usually conflict freeness. We expect to accept together arguments that do not attack each other. And admissibility, we expect to accept together arguments that are able to defend themselves against attackers. And from these concepts, we define classical extension semantics like stable, complete, preferred, and grounded. The purpose here is not to give a full catalog of extension semantics. So we will focus on these four semantics for the rest of the talk. So on an example, here we have an argumentation framework with 7 arguments and a few attacks. And depending on the semantics, we have different sets of extensions, and so different arguments that are accepted or not. For instance, the grounded semantics is very skeptical. So here we'll only have one argument A1, which belongs to the single extension. With the stable semantics, we also have one extension, but it's slightly more credulous because it does not accept one argument, but 4 arguments, A1, A4, and A6. And then with the preferred and complete semantics, we have, as you can see, several extensions. So this time we will have 2 kinds of reasoning modes. Either the skeptical acceptance, meaning that we accept arguments that belong to each extension for the chosen semantics, or credulous acceptance, we accept arguments that belong to at least one semantics. So for instance, if we look at the complete semantics here, we will have only one skeptically accepted argument, A1, which belongs to all the extensions. So here it actually coincides with the grounded semantics. If we look at credulous acceptance, we can see that we also accept A4, A6, and A3 because they belong to at least one extension. But there is one argument A5 here, which does not appear in any extension. So this argument is rejected here, whatever the semantics or whatever the reasoning mode, credulous or skeptical. So this famous model proposed by Dung has been enhanced somehow in different ways. And one of them that will interest us in this work is the addition of a notion of uncertainty in the argument framework. Here in particular, we focus on so-called incomplete argumentation frameworks, where there can be uncertainty about the existence of some of the elements of the graph. So here we focus on the model where uncertainty concerns the arguments. But as you see here, we talk about qualitative uncertainty. We don't have probabilities or things like that. We just have information that there may be an argument A4 that attacks A5 and A3 and is attacked by A3. Or maybe there is not this argument A4, but we don't have any quantitative measure of this uncertainty. And similarly for A7. So here, the other nodes and the edges are all certain information, and only the dotted nodes here represents uncertain information. And now, in order to reason with this kind of incomplete argumentation framework, we use the notion of completion. Intuitively, a completion of an incomplete AF is just a classical AF, which is compatible with the uncertainty encoded in the incomplete AF. So if you look, for instance, at this first completion, we had 2 uncertain arguments in the first incomplete AF, A4 and A7. So here, this is a completion where none of these arguments appear. Here we have A4, which belongs to the framework, but not A7. So if we take A4, we have to take all the attacks that concern it. But of course, since we don't have A7, we still don't have the attacks concerning A7. Here, it's the other way around. A7 belongs to the completion, but not A4. And finally, the last completion, all the uncertain arguments appear in the framework. And now, somehow it's similar to the fact that we can reason either credulously or skeptically with the set of extensions. We can also somehow reason skeptically or credulously with respect to the set of completions. We will look at acceptance with respect to each completion or some completion. So for instance, A1, we see that it's unattacked in all the completions. So for any of the semantics that we consider here, it will be accepted in each completion. So we say that it's necessarily accepted because it's in each completion, and of course, skeptically, because in each completion, it will belong to each extension. But we can also have some weaker form of reasoning with the credulous acceptance, but still in all the completions. So for instance, A3, it's here, for instance, it's skeptically accepted, but it's not skeptically accepted in all the completions, because here it will be credulously accepted. There will be one extension with A3, but also one extension where A4 is accepted and A3 is not accepted. So it's credulously accepted, but again, in all the completions, so it's necessarily credulously accepted. And as I said, we can also look at some completion instead of each completion. So A3, it's, as we just said, credulously accepted in all the completions, but it's also skeptically accepted in some completions. Here, the first completion and the third completion, A3 will be skeptically accepted. So we say that it's possibly skeptically accepted. And finally, the weakest form of acceptance here, possibly credulously accepted, for instance, for A4, because it's credulously accepted in the second and fourth completion, but not in all the completions. And again, we could say here that A5 is always rejected. No, not even, sorry, because it's accepted here. So A5 this time is accepted in some completions. So it's actually possibly skeptically accepted. Okay, so this is it for the background on abstract argumentation that we need in this work. Now I will introduce quickly a specific structured argumentation framework, which is a setting in which the notion of stability has been proposed in a paper last year. So it's inspired by the famous aspic plus formalism. We have a set of literals which is closed with respect to the notion of negation. We have rules that are divisibles, where here all the premises of the rule are literals, and the conclusion of the rules is also a literal. There is a specific set of literals that is called queryable literals. And regarding a specific agent, we have a consistent set of literals that is this knowledge base. And finally, we are interested in a particular literal from the language that we call the topic. And in the end, the notion of stability will be to know if this specific literal, the topic, can have different acceptance statuses when the argumentation setup evolves. So for constructing arguments from this kind of argument setup, we use some classical mechanism where an argument is actually a tree with as its roots a specific rule such that the conclusion of the rule is the literal that will be the conclusion of the argument. So here we want an argument for Q, so we will have a rule that allows to deduce Q. And then each child of this node will be either an element of the knowledge base of the agent. So for instance, if P1 is in the knowledge base of the agent, then we can just say that P1 is a child of this root node. But for P2, if P2 is not in the knowledge base, then we need another rule such that P2 is the conclusion of this rule. And then we iterate this process. For this new rule with P2 as its conclusion, we will need childs that either belong to the knowledge base or also rules from the argumentation setup. So with this mechanism, we can construct arguments for deducing some specific literals, and then we can define a notion of attacks between arguments, where an argument A attacks an argument B if the conclusion of the argument A is a negation of some literal that appears in the construction of the other argument. So all of these mechanisms are quite classical. And now what is specific to this work by Testerink, Odekerken, and Bex is the notion of status of a topic and stability of the setup with respect to this topic. So the status, we can have 4 different statuses. Either there is no argument at all in the setup that supports the literal to, so in this case we say that it's unsatisfiable. Then if we have some argument that belongs to the grounded extension of the argumentation setup, then we say that the status, the topic to is defended. If all the arguments that support this topic to are attacked by the grounded extension, we say that the topic is out. And in the remaining case, we say that it's blocked. And as I said, the notion of stability will consist in looking whether this topic will have different acceptance statuses when the setup evolves. So in order to formally define this evolution of the setup, we define the set of future argumentation setups as the set of setups, as you can see here, that are defined very similarly to the initial one with the same language, same set of rules, queryable literals, and of course the same topic. And the only difference is that we add new literals to the knowledge base because K prime is a superset of K. So simply a future setup is just, you take the same setup, but just add new literals in it. With these new literals, you can create new arguments and new attacks. And so you have a new grounded extension and possibly a new acceptance status for the topic to. And just now the notion of stability, it's the fact that in all future setups, the topic to has the same status, whatever we add in the knowledge base. Okay, so this is it for the background part. Now let us briefly motivate why we want to define the notion of stability in abstract argumentation. If we consider some example from automatic negotiation, or let's say more generally even strategic argumentation, at some point an agent may want some specific arguments to be accepted because it brings her some utility which is optimal. So the agent wants this specific argument to be accepted. Now, let's say credulously or skeptically with respect to one specific extension semantics. Here we are really abstract about what we actually mean by accepted. But if at some point the agent realizes that she will not be able to defend this argument at the end of the debate, it may be profitable to change our strategy before it's too late, because at some point what may be the optimal move for the agent in the debate, in the end may be something that will prevent her to have some profitable outcome of the debate. So let's give an example. We suppose here that 2 agents are negotiating about 3 offers which are supported by arguments P1, P2, P3. So we see here these arguments are mutually exclusive. And the first agent has preferences P3 better than P2, better than P1, and the other agent has the reverse preferences. So we suppose that the first step of the debate, agent 1 attacks P1 with A1, A2, A3. It seems reasonable because it defends P3 against P1. So it should help the agent 1 to make a preferred argument accepted. Now, without any possibility to look at the future, agent 2 may choose to defend P1 because P1 is a preferred argument. But let's suppose here that for defending P1 against A3, agent 2 has also to attack P2 because this new argument A4 attacks both these arguments. But now, if agent 2 is not able to defend P1 against A1 and A2, then whatever happens, P1 will be rejected because of these arguments. But now also P2 will be rejected because of A4. So in the end, agent 2 will be forced to accept the option P3, which is a least preferred option. So maybe it should be better to not try to defend P1, but to change her strategy and instead, for instance, attack P3. So thanks to the notion of stability, agent 2 here would be able to anticipate the fact that P1 will not be accepted, whatever she does. So it's better to change the strategy right now and defend P2 instead of trying to defend P1. So since this kind of strategic argumentation, and especially in negotiation debates, use different kinds of semantics and different kinds of reasoning modes, as I've introduced at the beginning of the talk, we want to adapt the notion of stability to reasoning with abstract IAFS in order to use it in this kind of scenario. So in order to here somehow have also a notion of future AFs that the agent will be able to look for deciding the notion of stability, we introduce what we call an argumentation universe. We suppose that for the application at hand, the agent knows the potential set of arguments that may be used in the debate and also the attacks between them. So any valid argumentation framework in this application will be made of a subset of this universe of arguments, and the attacks also, or all the attacks known in the universe that concern this subset of arguments. And now from this argumentation universe, we can also define the set of future argumentation frameworks. If at some specific moment, the agent's knowledge is represented by this argumentation framework F with arguments A and attacks R, then the future argumentation frameworks, or all the AFs built on this universe, of course, where the set of arguments is a superset of the set of arguments A. And now we can define naturally the notion of stability in abstract argumentation because we have as input our current AF, our reasoning semantics. We will distinguish between credulous and skeptical stability depending on the mode of acceptance for the arguments. And here, instead of having a topic, we will have a specific argument A from the initial AF. And so the question is it true that this argument is accepted, so as I said, either credulously or skeptically, with respect to the semantic sigma in all the future argumentation frameworks that may be built from this AF F. And now that we have defined this concept of stability in abstract argumentation, we will see that it's possible to check quite easily if an AF is stable with respect to some argument, thanks to existing work on incomplete argumentation framework. Intuitively, what we will do is from the AF and the universe of argument, we can build an incomplete AF such that the completion of this incomplete AF correspond to the future AFs. And so we can use some existing tools in order to solve the question of stability. So formally here, the incomplete AF will have the certain arguments that are the arguments that appear in the initial argumentation framework. So the uncertain arguments will be every argument in the universe except the ones which are certain arguments, and then the attacks in this incomplete AF or all the attacks in the universe. On an example here, let's suppose that this is our current argumentation framework, and we know that the argumentation universe is this graph. So now the incomplete AFs that correspond will be this one, where we have A2 and A1 that appear in the universe, but not in the initial AF. So they are uncertain arguments. And what we have shown in the paper is that we can easily check stability of an argumentation framework thanks to reasoning with the incomplete AF, because the argumentation framework is stable with respect to some argument, either if this argument is always accepted or always rejected. So always accepted, it means that it's necessarily accepted, either credulously or skeptically. So in all the completions, it's accepted. It means that it's accepted in the current argumentation framework and in all the completions that represent all the possible future argumentation frameworks. And on the opposite, if it's never accepted, it's not accepted in the current argumentation framework or in the future argumentation frameworks. So it's not possibly credulously or skeptically accepted. So we have looked at the question of computational complexity. We don't have yet full results, but we have upper bounds and lower bounds. And so to be honest, our guess currently is that probably the actual complexity is generally closer to the upper bound, but it's really just a guess. We have not looked yet at this question in details. So to conclude, by defining this notion of stability in abstract argumentation, we allow to generalize it to different semantics and reasoning modes, contrary to the initial papers on this topic, which only considers the grounded semantics for a specific structured argumentation framework. And we have seen that the existing work on incomplete argumentation frameworks allow us to easily compute to solve the question of stability in AFs. So there are several open questions for future research. The first one, as you can guess, is about the complexity, because we have only lower and upper bounds, but they don't coincide yet. So we hope to find tight complexity results. Also, it's interesting to look at labelings instead of extensions. It would be also closer to the initial definition of stability, where there were 4 statuses for the topic. Here we only have 2 statuses for an argument, accepted or rejected. So for instance, with the classical 3-valued labeling, we could look at in, undec, and out. Also, other frameworks that generalize Dung's framework are really interesting for this question. For instance, what happens if we integrate preferences in the argumentation framework, or supports, or even the so-called claim-based argumentation, where we have some kind of semi-structured and semi-abstract framework. So it would be also really interesting to bridge the gap between a purely abstract approach and the purely structured approach from the original work on stability. And finally, since I said we're interested in strategic argumentation, here it would be interesting in this, with this question in mind, to look at argumentation dynamics. So in a debate, an agent could be interested not only in knowing if the AF is stable at the moment, but also what should the agent change in order to make it stable with respect to a preferred argument. And I'm done, so thank you for your attention, and now I'm ready for questions or comments.
Hi, my name is Guilherme. I'm a PhD student at Imperial College, and my supervisor is Francesca, Toni, who's a co-author of this work with me. So in this work, I'm going to present, I want to propose a way of analyzing a classifier as a reasoning, a specific kind of classifier, but even then, we will kind of map classifiers in the sense of machine learning has an inference system, and you consider non-monotonic properties of it. Well, in particular, I'm doing this on this work for abstract argumentation for case-based reasoning. And in the paper, we propose a cautious monotonic alternative of it, which I'm going to present very briefly. So what is abstract argumentation for case-based reasoning then? It is a way of modeling case-based reasoning with argumentation, which exists in the literature quite recently. It's inspired by the legal domain. AI in law has typically used a lot of case-based reasoning and also argumentation, but using one of them for the other is something that has been worked with recently. And but some of those approaches, in particular the one we call AA-CBR, has been used as a classifier in some scenarios, in the machine learning sense, such as image classification, sentiment analysis in text, and predicting passage of views in the UK Parliament. So what do I mean by non-monotonicity properties? Well, the very classical ones, cautious monotonicity, which quickly reviewing is given you have a background knowledge K, and it's enough to derive a proposition A, and K is also sufficient to derive a proposition B. Then if you get A and you put it together with K, that you can still derive B. So you don't lose your inference power by adding inference conclusions that you already had. I'm also taking called cut, which is a kind of a converse of it. So K is enough to derive A, and K union A is enough to derive B. Then you don't need the A in the hypothesis to derive B. And cumulativity, which is satisfying both of those properties. And a very quick reminder of abstract argumentation, though that this might not be needed. We're working with arguments and relationship of attack, direct relationship, and we are going to use in this work the ground extension, which is basically checking which arguments are not attacked, considered them in, getting the attacked by those, considered them out, and then you check whether all of the arguments which are attacked only by out arguments and put them in and loop until convergence. Okay, so let's go to the heart of the matter. What do I mean by classifiers as reasoning? Well, I'm going to abstract, it's a very strong abstraction of classifier, has a function which receives a data set, which is a subset of all possible pairs of input, output. X here is my input set, and Y is the set of possible outputs. So I have here a data set, a finite subset of examples, and it receives a new case to be classified, so to return an output. So I'm abstracting classifier has a function in this way. And I define a language of positive and negative literals, and the positive literals are essentially pairs input output, and negative literals are negation of a pair. It's essentially just a syntactic mechanism of saying not X and Y. So what's the language, what's the inference relation I'm defining here? I'm defining a relationship between a data set to this language, to an atom. And the definition here is a data set infers using this classifier XY if and only if the classifier trained on this data set T and classifying X returns output Y. And it proves not X and Y. It infers not X and Y if and only if there is an Y prime such that CDX it concludes this predicts Y prime, and Y prime is not Y. It's different from it. So I'm basically formulating a classifier and giving an inference relation, and we're going to study the properties of this inference relation, which comes from the classifier. So a first result we have is quite strong result, which says that for the definition I gave, again, using the definition of the classifier I gave, infer C is cautiously monotonic if and only if it satisfies cut. And direct consequence of it is that it's cautiously monotonic if and only if it is cumulative. So either you satisfy one of those or you satisfy none of those for this kind of abstraction. Okay, so that's the general setup. And now I'm going to present what AA-CBR is. I'm not going to give the formal definition. I refer that to the paper, but I'm going to show by an example. It's an instantiation of a possible AA-CBR framework. So AA-CBR is a case-based reasoning that works in the following way. You have a case-based kind of past cases, which are pairs X and Y, input, output. Here I'm instantiating the set X has sets of features, and output is negative is minus plus, so it's a it's a binary classification, and it works in the following way: you give the cases, they become arguments in an abstract argumentation framework. Sorry, and you have a default case, which is an added case, an extra case. Here is an empty set with minus, and you have a new case, which is the thing you want to predict, has an argument as well. And the arguments are essentially defined in this way. The attacks are between cases are between past cases, including the default case, happens when the attacker is a superset of it, a superset of past case, and has a different outcome. So it's kind of it's more specific. Default case that has absolutely no information, and the other cases have more information and they attack, and they don't they don't attack back. And the new case attacks the ones which have features which are not in it. So in some sense, they are irrelevant. So I'm going here through an example in which I'm going to give an extremely simplified legal toy example of a legal system, which is, okay, let's consider whether someone should be sent to jail. By default, if you have absolutely no information, no one should go to jail. So that's the principle of the presumption of innocence. And that's represented here by the default case, saying minus. In the lack of information, you predict no. If the person, you have a past case which says, well, someone committed homicide, someone killed someone, and thus this person went to jail. Okay, fine. And another case is, well, someone stole something, so it's a theft, and this person also went to jail. So that's also a plus. And now we have a new case in which someone committed homicide, killed someone, but it was in self-defense. That's the new case. We have no past cases with reference to self-defense. And for this example, what the classification is? Well, homicide is relevant, so it's because it has a feature. It's not in the new case, so it's not attacked. But theft is relevant, so we attack for the new case, and the past cases attack the way they go, and you get then the ground extension, and you want to evaluate whether the default case is in the ground extension or not. Here it's not. I have shaded the ground extension, and thus the prediction for this is plus. So this person should go to jail. That's not what our intuition would like. And so if you have an extra case, which is, well, someone killed someone and it was in self-defense, and no, the outcome was this person did not go to jail, this person should not go to jail, then this case would attack the homicide and defend the default argument, and thus the prediction would be minus, as we would imagine. In general, A-CBR is defined, has in the paper, has a partial order, not necessarily has subset relationship, but here we are instantiating it with, as it was originally presented, has us between sets and the subset relationship. Okay, so one of the results is, well, A-CBR thing has a classification, has a classifier in this way, is not cautiously monotonic. Due to the interest of time, which I'm not sure I'm tracking correctly, I won't present I skipped the example, the counter example here, but you can refer to the paper. However, we can't define a cautiously monotonic variation of A-CBR, and that's what I'm going to present right now. So in order to present it, there is we need some helpful notions, and the first notion we need is the one of a surprising case, or a non-surprising case, which is, well, a case is surprising with respect to a data set if and only if, when we remove this case from the data set, if it's in there, the prediction of for this new case X is still Y, so it's the same prediction that we had before. So we don't need to have this in the data set, then you predict it correctly. So it's unsurprised. That's what we would expect. Otherwise, it's called surprising. So here an example, if we have this A-CBR framework here, ABC, well, we want to see whether ABC plus is surprising or not. And so we remove it from our case base, from our framework, and we consider it as a new case and evaluate it. And it turns out that outcome is plus. Since C is in the ground extension, the default is out, which is exactly what the case was. It's plus. So that's the expected outcome. Thus, the ABC is unsurprising. It's not surprising. And a quite technical definition we use as well is of a concise set. So suppose we're given a data set S, and a subset of it S prime, and we are interested in the function phi of S for S prime, which are exactly the cases in S which are surprising with respect to S prime. So all of the cases in this original data set S, which when you give S prime, you predict those cases, and okay, they are surprising. That's not what you would expect. We say that S prime is concise with respect to S whenever it's a fixed point. That is, S prime is exactly the set of arguments which are surprising to S prime itself, and only those. It doesn't, it's not missing any and contains all of them. And we also say that S or S prime is concise when it's concise with respect to itself. So it's its own universe, and all of its cases are surprising. So again, let's refer to the example. Is this set surprising? Is this set concise? Well, no, because as we saw before, ABC is unsurprising, and therefore this entire set is not surprising. But if we remove it, we can kind of quickly check that it is concise. Since if we remove each of A, C, or AB, or CD, the predictions would be different for each of them. Sorry, just so I check, how many minutes do I have left? Because I timed it wrongly here. Which time did it start? Hello?
You're muted. You're muted.
Sorry?
Bettina, you're muted.
Sorry, 8 minutes left.
Okay, cool.
Thank you.
Thanks. Okay, so, okay, given those definitions, why does this matter for ACBR? Well, ACBR has a very nice property, which is that given the spatial order, in the examples I gave subset, ACBR, well, the prediction for a new case X depends only on cases X prime, which are smaller than it. So quickly referring to this example here, for the prediction of AB, it only matters the A and the default case. All for the other, the ones which are not smaller are attacked by AB, and therefore they don't matter. So this gives a natural ordering based on the spatial order of the cases, and this allows a natural way of constructing concise case bases for ACBR. And what's interesting about it is that if you have a case base and you get the concise subset, which exists and is unique for ACBR, as it's also proven in the paper, then it is cautiously monotonic. Okay, so how do we do that more exactly? So the algorithm goes as follows. You start with your case base, your data set, and you topologically sort it. That is, you sort respecting the partial order. You extend the partial order to total order, how you prefer. You start with an empty case base, or actually just the default case. And for each case in the topological order, following the order, you do the following. You just check if this case is surprising with respect to the current CB or not. If it is, then you just add it. Otherwise, you don't. And that's the end. It's very simple. Since you have an ordering, you just follow along the ordering and you're done. So a quick example, suppose we have already done this for A, C, and AB, and CD, which, as I said before, is concise. And you are now checking for ABC plus and for ABCZ minus. Well, okay, so for following the ordering, ABC is smaller, so we need to check this first. And as we did in the previous example, the predicted outcome here is plus, which is exactly this one in the case base we're processing. And thus it's unsurprising. Therefore, we just do not add it. We just throw it away. And now we have ABCZ minus, and let's check again. It's very similar. The prediction is here is plus. And therefore, the predict outcome is different from the case in the case base, which is minus. Therefore, it is surprising, and we have to add it to the case base. And that would be our final case base, adding the ABCZ minus case. Just some quick considerations on this process. This is a simplified presentation. The one in the paper is a bit more involved, but it's just so that we can have some gains in complexity and specifically on parallelism. But the core of how it works is essentially the same. And we have proofs that the one on the paper and also this one here has a consequence. It terminates and is correct. So in summary, I think I've gone somewhat fast, but it's okay. We can study classifiers as reasoners. Just some quick considerations. I've done, again, a very specific abstraction of a classifier has a function, and in particular has a total function. This does not take account for partial functions for lack of determinism, but these are issues left for future work. You can always kind of tweak simply, for instance, fixing a random seed or these kind of things. But the general gist of it, we can study classifiers as a reasoner. Since you have a reasoning system, an inference system given the classifier, you can, it's well defined for you to say whether the classifier is cautiously monotonic or not. For those which are not, some of them, at least for the case of AA-CBR, you can define a cautious monotonic version of it. So for future work, what we have left is empirical comparisons. So this work was entirely theoretical. You have only the proofs. In particular for performance, for time and space complexity, and for explainability. On the current experiments, we have checked that usually the case bases for AA-CBR, well, after the processing, are much smaller than the ones for AA-CBR, which basically just accepts anything. And likely this impacts not only for time and space complexity, but it's also a good property for explainability, especially for visualizing the argumentation framework. Instead of having hundreds or thousands of arguments, you have much less, 10, 20, or 30 on that order. And okay, another future work is seeing whether this kind of analysis can be properly used for other classifiers, but that's not something we have touched upon or plan to see soon. But well, let's see. Thank you.
So yeah, the title of the paper is basically straight to the point. So weak admissibility is semantics, and PSPACE is a complexity class. So obviously, this kind of already shows you the main result of the paper. Yeah, but maybe I should start with motivating and explaining weak admissibility. So this is some general stuff about argumentation frameworks and admissibility. So I think it's not really necessary to explain this in detail here. Of course, an argumentation framework is a directed graph, and the goal is to formalize which arguments one deems acceptable and which not. And a quite popular approach is admissibility, with the requirements you probably all know, namely that the target set is conflict-free and it's able to defend itself. So for example, in this case, we have that A and D is admissible because, of course, A is defended against the attack from C by D, D defends itself, and that's it. But already Dang in his famous seminal paper pointed out there is an issue with this notion, which is that in certain situations, dummy arguments which attack themselves might block the acceptance state of reasonable arguments. So for example, here we have that A is self-attacking and blocks B, although one might expect that B should be deemed acceptable in this case because it's not challenged by a serious attacker. The same is true here, where this odd cycle is basically not really meaningful, but blocks the acceptance state of B. While on the other hand here, of course, C resolves this, this conflict here, and thus B should not be acceptable. And in a recent AAAI paper, we tried to come up with a solution to find the semantics which behaves in this way, which is shown here. And this is called weak admissibility. And the idea is as follows. We pick a target set of arguments, and then we want to know, is it attacked by a serious attacker? So is it attacked by a meaningful attacker, or is it not? So we do not care for all attackers, but we care only for the attackers we deem meaningful. And in order to formalize this, we consider the reduct with respect to an extension. And this works as follows. We take our target set E, and basically we remove E and the range of E from the initial argumentation framework, which is of course motivated by the idea that if you fix E, then the arguments in E are considered accepted, and the arguments which are attacked by E are considered rejected. And this reduct contains all the arguments which are then still in the game, so to speak. So for example, here, if I consider B and then I remove B in the range, then A is left. Similarly here, the odd cycle is left. And in the last example, well, because it's actually a stable extension, C and A3, then the whole AF is gone. Okay. And so now the idea, like I just said, E is considered accepted, E plus is considered rejected, and now we have this remaining AF, and now the question is, what shall we do about it? And like I already said, we want to accept E if it's not attacked by a reasonable attacker in the induced reduced AF. Okay, and to formalize this, now the question is, again, given this reduced AF, which arguments do we accept and which arguments do we not accept? And we decided that it's probably the best if we decide this in a recursive fashion. And so that's the motivation for the following definition. A set E is weakly admissible if it's conflict-free, and in the corresponding reduct, there's no set E prime, which is weakly admissible in the reduct and attacks our target set E. All right, and this definition manages to exactly put out, or not exactly, but manages to find these admissible or weakly admissible sets. Here is it B, here is it also B, and here it's C and A3. Of course, there are some more weakly admissible extensions, but these are the ones we really care about. Okay, so now after briefly explaining weak admissibility, let's talk about the complexity. So like I said, as the title suggests, reasoning with weak admissible semantics is PSPACE-complete. And the first step is to try to give some intuition why this is the case. And the problem is, or one of the problems with the semantics, or not really problem, but reason for the high expressive power is, if we consider, for example, this simple AF, A1, A2, A3, A4, and we want to know whether A4 is weakly admissible or not, then we have to consider the reduct with respect to A4. And what's happening then is we have to check or in order to verify whether or not A4 is weakly admissible, we have to look at the attacker A2, and we have to decide whether this attacker is weakly admissible in this reduct here or not. And now the point is that A2 in this AF, A2 is not weakly admissible because it is attacked by A1, which clearly is weakly admissible. And so A4 is weakly admissible because it's defended by A1, but we do not even need to put them together in one extension. So the weak admissibility semantics already has some kind of look ahead or does some extra calculation and identifies A2 as an argument which is to be rejected, and hence A4 alone is weakly admissible. So, and this means, well, that's why it's not really a local property as opposed to classical admissibility, where you can basically look at the target set and the surroundings and which arguments are attacked and so on. And then you can basically make a fast decision whether you have an admissible extension or not. This is not really the case here. You are really forced to have a look at the complete reduct. In worst case, you have to compute several sub-AFs because if you want to know, for example, if A2 is weakly admissible, then by definition, you have to compute another reduct and so on and so far. And the only hope is, so to speak, that at least for credulous acceptance, you might find a shortcut if you do the right guess intuitively. Because in this case, if I want to know whether A4 is credulously accepted, of course, I'm not gonna pick A4 and check this nasty recursive definition. I would just pick A1 together with A4, and then I found a stable extension, which of course is also a weak admissible extension. Yeah. However, as the main result of the paper shows, in general, there is no such shortcut, and all the standard reasoning problems are PSPACE-complete. And starting with membership, this is actually not so hard to see because PSPACE is a quite expressive class. So a generic algorithm to see this is as follows. If you want to know whether a set is weakly admissible, just check whether it's conflict-free or not. If it's conflicting, you can return false. Otherwise, you compute a reduct. You iterate over all sets of arguments occurring in the reduct. And if one of them is weakly admissible, then your target set is not, otherwise it is. And of course, the third step requires to compute several sub-AFs, but at any point you only need to store the current target set. So this is a PSPACE procedure. Now for the hardness, this is actually where it gets interesting. And to warm up a little bit, I have brought to you the standard construction which shows, or which is used to show, that classical admissibility is NP complete, yeah, or in this case this is the hardness part. So what do you do in the standard construction? You reduce SAT, so you have a formula in CNF, like for example these three clauses. And then you construct the following AF. Here you have the variables attacking each other because they are exclusive. And then a variable attacks a class if it's contained in the class. So if all these clauses are satisfied, then your target set T or argument T is defended. And hence it's quite easy to see that by construction, T is credulously accepted if and only if our formula phi is satisfiable. Yeah, and the underlying idea is that the chosen arguments, they correspond to assignments, and the defeated C arguments, they correspond to the satisfied classes. And yeah, we thought about this for a while, and of course, this is some reasonable starting point. for any hardness proof in reasoning in AFs. But for the weak admissibility, we had to come up with some adjustments. And so let's see. The first step we had to do was we built a chain. Yeah. So the idea is that given an arbitrary QBF, so as you know, I did not put it on the slides, but as you know, the generic PSPACE-complete problem is deciding for an arbitrary quantified Boolean formula whether it's evaluates to true or not. Yeah. So you have an QBF here with just one quantifier alternation. So that suffices to show you how the construction works. So all I'm gonna show you, you just need to make it longer, yeah, and then you have the construction for more quantifier alternations. So what do? We take the variables and we build such a layer-ish chain here. We have x variables, x2 variables here, x1 variables here, and like I said, if you have more variables, just build a longer chain. Yeah. And now what's happening? Assume you want to decide whether phi is weakly admissible or not. Then by definition here, it says no attacker of phi is allowed to be weakly admissible, which is basically a universal quantifier because we have to verify that for all attackers, which are in this case x2 and bar x2, for all attackers here, we have to check whether that they are not weakly admissible. And so the formula has an universal quantifier here because it's just there. So that's the logic of the formula. And this translates to the semantics because this recursive definition requires us to check both x2 and bar x2. Okay. And in the next step, we have an existential quantifier here. And this translates to the semantics of our AF because, well, say we pick x2 here, and then phi is acceptable if x2 is not. And what does it mean to show that x2 is not weakly admissible? Well, there has to be at least one attacker of x2 in its corresponding reduct. And this is this existential quantifier here. So either x1 or bar x1 has to be weakly admissible in order for x2 to be not weakly admissible. And if both x2 and bar x2 are not weakly admissible, then phi is. Yeah, so this logic is basically going back and forth if you move here from left to right. Okay, so that's the first step where we build our chain. Now, of course, this has nothing to do with the formula so far. So we also need to add the classes. And this works as follows. The first thing is probably quite expected. So the variables attack the classes in the natural way. So if, for example, x1 occurs in C1 here, that's why x1 attacks C1. Similarly, x2, for example, attacks C2 because the x2 variable occurs in the second class. Yeah, and the part which is a bit novel here is that the C classes, they do not attack phi, as it's the case in the standard construction, but they actually attack the last layer of X variables. So they attack X1. So C1 attacks both X1 and bar X1, and C2 attacks both X1 and bar X1. So and this appears a bit random, but hopefully you will see quite soon why this makes sense. Because we can start again with phi. Okay, let's do the same again. Yeah, we want to know whether phi is weakly admissible. What do we have to do? We have to check that both x2 and bar x2 are not weakly admissible. So we check with we start with x2. To see whether or not x2 is weakly admissible, we check is there either x1 or bar x1, which is weakly admissible. And now if we build the reduct with respect to x2, then c2 disappears because it occurs in the formula and it's a text c2. And now x1 is actually weakly admissible because it attacks both bar x1 and c1. So if I build the reduct with respect to x1, then nothing is left. So, and in the empty AF, of course, there is no weak admissible attacker of x1. Yeah.
Sorry, Markus, you have 2 minutes left.
Okay, all right. Yeah, I think I can manage. So there's no attacker left. And so hence x1 is weakly admissible. Yeah, and that's why x2 is not. Yeah. And if we try again with bar x2, then we go from left to right. I speed up a bit because there's not much time left. And then no matter whether I pick x1 or bar x1, both of them are not weakly admissible. And that's why in this case, x2 would be weakly admissible, but phi is not. So, and now finally, I'm not spending so much time now anymore. Because what we now need to do is we need to make sure that this construction actually always works the way I just explained, because there's always the possibility to pick other weakly admissible extensions than the ones I just showed you. And that's why we have some auxiliary arguments which induce out cycles to make sure that it's always happening in the way I just explained to you. So there are really no other extensions than those I just showed you. And we need a couple of additional assumptions on our QBF. Namely, it has to start with a universal quantifier and with an extension quantifier. And we only allow one variable per quantifier alternation. But this is all no problem because we are in p-space. And since we can make our QBF of arbitrary length, these assumptions are not really restricting anything. And so that's why I come to an end. And this was the verification problem, of course. And if the verification problem is p-space complete, then you expect everything else also to be p-space complete. I did not talk formally about weakly preferred, but as in the classical case, weakly preferred are just a subset maximal weakly admissible semantics. And as you can see, everything's p-space complete except the trivial case of skeptical acceptance, because like here for classical admissibility, nothing is skeptically accepted ever. So that's trivial. All right, so that's it. I hope this was not too long now.